Okay, first I want to say, of course, that we are really grateful for receiving this award. Since we got the notification, we are all pretty excited about it. So thank you for this recognition of our work. As the title says, it is about abstract argumentation. And maybe I start with the first motivation here. Argumentation frameworks or abstract argumentation frameworks are a framework to model debates or exchange of arguments from agents, and they are usually just abstract argumentation frameworks are usually just directed graphs where the nodes represent arguments and the edges here model the attack relation. And now you have this argumentation framework, and you want to decide formally which arguments do you want to accept and which do you not want to accept. And to achieve this, several so-called semantics have been proposed in the literature. And one very important concept is this of admissibility. And a set of arguments is admissible if it satisfies two quite basic conditions. It has to be conflict-free and it has to defend itself. So for example, one admissible extension of this argumentation framework is A and D, because D can defend itself against the attack from E, and it defends A against the attack from C. Yeah, and they do not attack each other, so they are also conflict-free. And this is basically the very basics, so to speak. And now, however, there's a problem with this notion, because as you can see here, it might be the case that an argument which can be considered a dummy, which is attacking itself, might attack another argument B, and so in this way block its acceptance state. Although B can actually be considered quite reasonable, because the only attacker of B is a self-attacking dummy. And this was already pointed out by Dung in his seminal paper, 1995. And he said, this is an interesting topic of research. And yes, we agree. So we had to look into this and we came up with the following idea. So we do not want to drop defense completely, but we want to require defense only against meaningful attackers. Yeah, with the attention that in this example, of course, A is not considered a meaningful attacker. More specifically, we want here B to be acceptable. We also want B here to be acceptable, because this odd cycle represents some dilemma and there's no really decision to be made here, and B should be able to be acceptable. However, in this case, we do not want B to be acceptable, because here this conflict is resolved by an additional argument. And the way to formalize this works as follows. We pick a candidate set E of arguments. We fix the set and we assume, okay, now we know which arguments we accept and which arguments we reject, because certain arguments are attacked, of course. And then we have a look at the remaining argumentation framework. And this is formalized by the so-called Reduct. Yeah, this is the AF. After we remove our extension E and all the arguments which are attacked. So if you're familiar with argumentation frameworks, this is usually called the range of E. And for example, the range, the reduct with respect to B here is just the self-attacker. Here it's just the odd cycle. And another example where actually something happens, if you calculate the reduct with respect to A3 here, then you remove B, you remove A1, you remove A3, and the remaining AF is C, which attacking A2. And now the idea for this weak admissibility semantics is that via a recursive definition, we consider the reduct, and then again, we decide which of the arguments we deem reasonable in this reduct, and then we can calculate whether or not our target ZE is attacked by a serious counterattacker. And I'm not going into details here, but what you should take away is that this is a weakening of admissibility, trying to formalize that only meaningful attackers are to be considered. So what we realized, however, is that this notion of the reduct is actually quite fruitful. So first of all, it's possible to characterize the standard Dung-style semantics quite easily in terms of the reduct. For example, an admissible extension is just a conflict-free extension, and in the corresponding reduct, there shall be no attacker of our extension. Yeah, or another prominent semantics is stable extensions, where you require it must be conflict-free and it must attack all other arguments in the AF, which in this case simply means the reduct is empty. However, the most exciting property we found with respect to the reduct and we formalized is the so-called modularization property. And for this, we can, for a second, catch a break of all this technical notions and formal ideas, and we can just have a look at an example. Yeah. So suppose you are living in Europe and you are planning your vacation. Obviously, you're not planning your vacation right now, so imagine it's probably 2022 or something. Yeah. And you have not decided yet whether you want to go to Paris or to Las Vegas, having a bit of a party, or you want to travel by train or by airplane. However, of course, starting from Europe, if you decide for Vegas, going by train is not really an option, so Vegas attacks the train. Now, if we construct the reduct with respect to Paris, because we decide to go to Paris, yeah, then both train and airplane are still an option. Yeah, you have not yet any constraint imposed of whether you go by train or you go by plane. And what we thought is that an argumentation semantics should respect this. Yeah, so if we do not make any assumption about whether we go by train or by plane when we decide for Paris, then it should be possible to consider both Paris and train and Paris and plane as extensions. And this compatibility property is formalized as follows. Yeah? We say a semantic satisfies modularization if, well, whenever we are given an extension, and we are given another extension with from the corresponding reduct, then we can basically put them together to find a novel extension. So like in this case here, Paris together with train or Paris together with plane. Yeah. And we quickly realized that the standard Dung semantics, they all satisfy this modularization property. Although this was never mentioned explicitly, so Dung never really mentioned the reduct explicitly, so it was kind of surprising that it works for all these semantics. However, moreover, we found that using this modularization property is actually quite a powerful tool, not only for with respect to the proofs. So there are many results which rely on, or whose proofs rely on this modularization property, but also they are quite capable of characterizing semantics, or at least the acceptance of semantics. And one example is here. Suppose you have any semantics, yeah, and you credulously accept unattacked arguments, which is quite a soft requirement, yeah, and it also satisfies the modularization property. Then this already suffices that your semantic sigma is forced to accept all arguments which occur in the grounded extension. So if you are not familiar with the grounded extension, you can just think of the most cautious, the most skeptical way to reason about argumentation. So nearly all standard semantics proposed in the literature are supersets of the grounded extension. So this is really a very basic requirement. And you are already forced to accept all the arguments in the grounded extension if you accept unattacked arguments and respect the modularization property. A bit deeper is the next result about strong admissibility, which can be thought of a refinement of the grounded extension. So you do not only accept the grounded extension, but there are also some subsets of the grounded extension accepted. And we have the following. If you have a semantic sigma and it not only it accepts unattacked arguments, but also any subset of unattacked arguments, and it satisfies modularization, then you're already forced to have any extension which is strongly admissible in your semantics as well. And now I want to come back to weak admissibility, because this is where the exciting part starts. Because we observe that naive semantics, they are just maximal conflict free, so they do not have any notion of defense. They do not satisfy this modularization property, and it's actually quite easy to see this. You can just take an vanilla outcycle, pick an arbitrary argument A1. This is a naive extension. But if you compute the reduct, then you have A3, but you cannot put them together in this modularization fashion because now you have a conflict here. So this is not working. So the question is if admissible-based semantics tend to satisfy modularization and naive semantics do not, is there some kind of minimal requirement? So what's the least you have to do in order to satisfy the modularization property? And here's where weak admissibility comes into play again. So remember, weak admissibility was this novel semantics trying to not ignore defense, but restrict it to situations that matter, so to speak. First of all, weak admissibility satisfies modularization. However, more importantly, given an arbitrary semantic sigma, if it is conflict-free, which is a really basic requirement. So really the vast majority of approaches in the literature are conflict-free. So this is as close to no requirement as you can get. If it is conflict-free and satisfies the modularization property, then if you are having all the weakly admissible extensions in your semantics, then you are already forced to coincide with weak admissibility, or the other way around. Weak admissibility is among the most liberal semantics satisfying this modularization property. So it's not the greatest semantics satisfying modularization. This does not exist, but it is a maximal semantics satisfying modularization. And this was really, really surprising and really exciting to us, because this weak admissibility is not tailored to satisfy this property or something. It's tailored to reduce the impact of self-defeating arguments. So this connection here was really cool to explore. All right, now to come to an end, I have some further aspects at a glance. First of all, here are some desirable criteria which are proposed in the literature, and we investigated them with respect to our novel semantics. Of course, all those which are here, they are results from the literature. And what I want to mention is that two things I want to mention. The first is the modularization property is satisfied by almost all semantics here. So it appears like this is quite a generic property, and this makes it all the more surprising that it's so capable of characterizing the behavior of semantics. So you would not expect this from a property which seems to be so generic when it's satisfied by almost all semantics. And the second thing I want to mention that as far as I'm aware, we have a question mark here and here with some semantics I did not really discuss. And I want to mention that in a recent comma paper, there are counterexamples found. So just assume you have a cross here, but this was not in our paper. And finally, we also considered strong equivalence. So I feel obliged to talk about this because it's in the title of the paper. As is usual for a non-monotonic framework, we say two argumentation frameworks F and G are strongly equivalent whenever they have the same semantics, no matter how much attacks or arguments we add to both of them. And now there are approaches in the literature how you avoid to compute like infinitely many AFs in order to check this condition, because there are results where you identify some redundant attacks, and then the idea is that F and G are strongly equivalent if and only if they coincide after removal of these redundant attacks. So the research here is driven by finding those redundancies. And we found those by having a look at a recent AAAI paper where, which says that the weak admissibility-based semantics, they do not change when we remove a self-attacking argument. And so for our strong equivalence investigation, this is important because, for example, if a self-attacker attacks an argument, or if an argument attacks a self-attacker, or if they attack each other, then we now know these are all redundant attacks because we can ignore self-attackers. So for our strong equivalence, we are interested in the following. We can remove all in and outgoing attacks of self-attacking arguments. Of self-attacking arguments. So F and G are strongly equivalent if and only if they coincide after we removed all these in and outgoing attacks of self-attacking arguments. Okay, so I know this was very brief. Of course, there are more details in the paper. So I think now the coffee cup is almost empty. So it's time to thank you for your attention.